So what were we talking about? We were talking about angular momentum. So far, our definition of angular momentum for any rigid object was, if I had a rigid object rotating around some axis with omega, and the moment of inertia around that axis is I, then L was I equals I times omega, right? And why was it a useful quantity? It was a useful quantity because if I have a closed system, which means there is no external net torque, L total is conserved. Right? You actually, again, intuitively know this from daily experience. I mean, one example I gave was divers. When they jump off a cliff, they try to minimize their moment of inertia so that they can actually tumble more times. They can rotate more times. Another example from daily life, you actually know, is maybe you haven't thought about it, but a helicopter. So that's my terrible drawing of an helicopter, right? Now, there is the blade, which, I mean, up in the air, the helicopter is pretty well isolated system. Okay. So what happens if you actually change the speed of rotation of your rotor blades? If your total angular momentum is to be conserved, that would mean the helicopter body will start to rotate in the other direction, right? For total angular momentum is to be conserved. And you certainly don't want that. So that small fan here actually just gives you the torque so that your helicopter body doesn't rotate. Okay. Actually, if you want to shut down a helicopter, it turns out this is the weakest point of the helicopter. If you can turn off that blade, then the helicopter body will start rotating because total angular momentum is conserved. Okay. But these are small helicopters. You know, there's a big, in Beytepe, there's a big military place, right, close to our campus. And you can actually see helicopters taking off and landing there. But most of them are these big cargo helicopters. I don't know how to draw them though, right? Which have two blades. And if you actually look at them carefully, you'll see that their sense of rotation is different. One is rotating one way, the other is rotating the other way. So that total angular momentum is conserved. Okay? So you don't want to rotate the helicopter body. Actually, it also gives you a nice way to orient your helicopter. If you want your helicopter body to rotate, you just change the rotation frequency of one of the blades with respect to each other so that you can actually rotate by any angle you want. And do any of you fly drones? It's very popular. Quadcopters. Why do you think there are 4 blades in that? 2 of them, I mean, check it out if you're actually flying any of those drones. 2 of them are rotating one way, the other 2 are rotating the other way. And again, by changing their frequencies, you can change the orientation of the drone. That's how it's accomplished, okay? So angular momentum conservation is, again, something very logical, very intuitive from our daily life. But maybe the last thing we discussed in the previous lecture was maybe our definition was too restrictive. Now, why is that? Let's talk about a simple example. So I have a 9-year-old son who really likes going to playgrounds. Okay, and one of the most fun devices on a playground is basically just a, so I'm looking at it from the top. It's basically just a platform which can rotate more or less frictionless around the pivot point, around its center. So what happens when I'm looking at it from the top, right? So what happens if a child runs with velocity v and jumps onto the platform? It starts rotating, right? So if total angular momentum is conserved, somehow, even before he jumped onto the platform, there must be some angular momentum carried by the child, right? So even an object moving with constant velocity can carry angular momentum. And here is why you have to be careful about angular momentum. When I talked about momentum conservation, I did not say momentum with respect to an axis or with respect to some coordinate system. Momentum was defined, or momentum was conserved for all coordinate systems. However, when I'm talking about rotation in general, I must almost always specify with respect to which axis I am defining my quantities. You remember, moment of inertia actually depends on where that object is rotating around, around which axis it's rotating around. It's the same thing with angular momentum. Angular momentum is defined with respect to the rotation axis. So again, maybe the same example, let's make it actually simpler. Now I know that if I have a mass m that's coming with velocity v, if this object hits that freely rotating disk, what will it cause? It's going to cause rotation and the counterclockwise sense. What happens if I send the object with the same velocity, but on the other side of the axis, if you want? What will happen? Well, it will actually cause counterclockwise rotation. And similarly, if I just send it on axis, it's not going to cause any rotation, right? So let me give you a new definition of angular momentum. I'll say angular momentum of any object is this r vector, which is the vector from the pivot point to the object, okay? Cross product P. Now, let's see if this makes sense. First of all, why do I have a cross product? What is the angular momentum imparted onto this platform if R and P are in the same line? You remember, cross product was magnitude of two vectors times sine of the angle between them. That's 0 in that case. So if I am on axis, I cannot impart any angular momentum. Okay. But so it makes sense. If my angle theta here is larger, then I'll actually give more angular momentum, right? How about the direction? R cross P. For the upper object, R is this vector, right? I still have the freedom to orient my palm. I orient it so that I can close my 4 fingers to the second vector, right? So R cross P for the first object is out of the screen. Out of the screen means counterclockwise rotation. How about for the lower object? That will be R. My R vector is here. I can still orient my palm. I orient it so that I close it towards the second vector. So R cross P is into the screen, which means clockwise rotation. You're using your left hand. Be careful. Okay, so so I mean, repeat this, but be careful. Most of you are right-handed. In the exam, that people really tend to do this, which gives you just the opposite result. Question? Sorry? Which hand will be used? Oh, it's the right-hand rule. Okay, it's always the right-hand rule. Be careful. Remember that cross product is the right-hand rule. Okay? Can you repeat this? No? Let's do R cross P once again. So for the first object, this is R. And this is P. Right? For the upper object. What was our rule for cross product? I take my 4 fingers, orient them along the first vector, R. So I still have the freedom to rotate my hand. Which way should I rotate it? I rotate it so that I can close my hand towards the second vector. So my thumb points along R cross P. Okay. If you're having trouble here, in Physics 102, you'll have much more trouble. Okay. We'll have 4 different right-hand rules in Physics 102. So R cross P. Oh, careful. Louder again, I could not hear you. There are different versions of right-hand rule. All of them amount to the same thing. Okay? So, yes, you can do that. I mean, another way is to use these 3 fingers. But I actually like I actually like my version. So, yes. Yes, that's very important. Now, L is R cross P, which is not equal to P cross R. So that was one thing that was important about cross product. Ordinary multiplication is commutative. You can change 5 times 3 is equal to 3 times 5. But vector multiplication actually depends on the order. It turns out R cross P is exactly minus P cross R. So it's anti-commutative. Right? Which actually means if it's out of the screen, angular momentum means counterclockwise rotation. All right? Let's solve one example. Let's say that I have a uniform rod on a frictionless table. Fixed at one end, but free to rotate. So that's my pivot point. It can actually rotate around that point. Let me close the door. Now, let's say that I'm sending a mass m with velocity v, and the total mass of this rod is m, and its length is L. And this object is exactly going to hit to the center of my rod. After the collision, the mass sticks to the rod. So if this mass sticks to the rod, what will the system do? We intuitively expect it to start rotating with some angular frequency, angular velocity omega. So I would like to find, first thing I would like to find is this rotation frequency. Second thing I would like to calculate is energy lost during collision. All right? Now, first of all, what should be our guiding principle here? Let's think. We need a conserved quantity, right? Because we are going to describe the collision process, and collision process, we don't really know what kind of forces are at play during the collision. It's a very violent process, right? So we need a conservation law. First of all, is energy conserved? No, it's not conserved. Why is it not conserved? Because during the sticking, there would be some, and we are not said this is an elastic collision. Instead, it's a completely inelastic collision where these two objects actually stick to each other. So energy is not conserved. How about momentum? Do you think momentum, not angular momentum, momentum is conserved during this collision? How many of you think it's conserved? How many of you think it's not conserved? How many of you are still sleeping? Okay. Momentum. Okay, so we said energy is not conserved. And momentum. What was our condition for momentum conservation? There should be no external force acting on my system. Now I see my system here. There is a rod and there is a mass. So it looks like a closed system, except that here there must be some nail or screw, something which holds my rod tied to the plane, right? So during the collision, that screw may react. It must actually give some force so that my rod actually does not go away. So because of that force, this is not a closed system. So because of that force, momentum is not conserved. If I had a freestanding rod, no nails anywhere on it, then momentum would be conserved. But now it's not. How about angular momentum? Is this a closed system? I just told you it's not closed system, but that was with respect to momentum. For momentum, our definition of a closed system was there was no external force. We just saw that there is an external force. However, if I actually fix my axis here, can this force create a torque? It's being applied exactly to the pivot point, right? So angular momentum, it turns out, is the conserved quantity here. Maybe I should repeat this logic once again, okay? So maybe it's our shortcoming of our nomenclature. Okay. Closed system can mean two different things. One thing is that there is no net external force on my system of particles. That would mean a system for which momentum, linear momentum, is conserved. On the other hand, sometimes when I say closed system, I mean closed with respect to angular momentum, which means there is no net external torque on the system. Okay. Which one is this? I told you that there is a nail fixing my rod to the table, right? And during the collision, that nail will give a force so as to keep that rod flying away, right? It's fixed to the pivot point. So there will be a force applied on my rod exactly at its end by the nail. That is an external force, so my system does not conserve momentum, but that force cannot cause a torque. It's applied to the pivot point, so net torque on my system is 0, which means angular momentum is conserved. Okay? Good. So what's my initial angular momentum? Initially is any angular momentum coming from my rod? No, it's not moving, so there is no angular momentum coming from there. How about angular momentum coming from this mass, small mass? If this is r and this is m times v, I think there will be a counterclockwise angular momentum here, like r cross p gives me out of the screen direction. How about the magnitude of initial angular momentum? So this is going to be m times v times r times sine theta. But what's r times sine theta? Here I have a nice right triangle. So this is r sine theta, which is equal to L over 2. Okay. So m v L over 2 is my initial angular momentum. How about in the final case, what's my angular momentum? Let's be careful. Again, I have two contributions here. My rod is rotating, but also my small mass is rotating, right? So in the final case, what is the contribution coming from the rod? It's going to be I rod times omega, and here I edge for a rod was m L square over 3. Okay, you could look this up or remember it. But there is another contribution. Again, I should write m times v cross r, or r cross m times v. But what is v here? If this length is L over 2, v must be omega times L over 2. What's the length here? Again, L over 2. So m times, let's do this, it's r cross p. R has so I rod, I already wrote, is m L square over 3 times omega. R is the vector from the pivot point to the mass. It's going to be L over 2. P is m times v, but v is omega times L over 2. The angle between momentum and r is 90 degrees. Sine 90 degrees is 1. So that's it, right? Now let me write this in a slightly different form. Let me write this as I rod plus m L over 2 square times omega. Okay. So what does that look like? It's actually the moment of inertia of the full object, this small mass m attached to the rod, right? What was our rule for calculating moment of inertia? It was integral r square dm, or integral sum over r squares times m. So this is exactly m times how far away it's from the pivot point squared. Okay. Now I can finish my solution. I can say that my initial angular momentum is equal to my final angular momentum. Initial angular momentum was mv L over 2. Final angular momentum is ml square over 3 plus small m L square over 4 times omega. 1 power of L I can cancel. So omega is m v over 2/3 m plus small m over 2 times v divided by L. Okay? Now, let's check. Did I reach my goal? Well, not yet, right? Because the question also asked me to find the energy lost during collision. So, can you tell me the initial energy? What's the initial energy? This is on a horizontal table, so there is no need for potential energy. There is only kinetic energy. What's my kinetic energy here? 1/2 mv square. How about in the final situation? I can calculate it two ways. I can either say I'll have the rotational kinetic energy of the rod, 1/2 I rod omega square, plus 1/2 mv square of the small mass. Or I can say, hey, now my system is combined with a new moment of inertia, I system. So this must be 1/2 I system omega square. Okay? So let's compare these. E initial is 1/2 mv square. How about E final is 1/2 times ml square over 3 plus ml square over 4 times omega square. Now I can write omega. I have already found it. 1/2 m over 3 plus small m over 4 times L square. Omega square is capital M square divided by 2m over 3 plus m over 2 squared v square over L square. L square is cancelled here. 1/2 m squared. Now I have m over 3 plus small m over 4 upstairs. And here I can take a factor of 2 out. So 4 times m over 3 plus small m over 4 squared times v squared. 1 power of that goes away. So this is 1/2. Let me write it in a different way. M v square times m divided by m plus 4/3 of capital M. Which one is larger, initial energy or final energy? initial energy is 1/2 mv square. Final energy is 1/2 mv square times a factor which is less than 1, right? Small m divided by small m plus a positive quantity. So that's good. Delta energy is E initial minus E final. That's the energy lost. It's going to be 1/2 mv square, 1 minus m divided by m plus 4/3 m. So 1/2 mv square, m's cancel, 4/3 capital M divided by m plus 4/3 capital M. Or if you want, let's get rid of these 3's and write them. Okay? Question?
Can you write the final energy separately, not using the system?
Excellent. Let's do that. Let's see if it actually gives me the same thing. I'm writing my final energy in a different way. I'll say my E final is 1/2. What's I rho? I rho is m L square over 3, right? Times omega square plus, what's the kinetic energy of small m? 1/2 m v square. But what's v? V is omega times L over 2 square. Okay. So if I combine these, I'll actually once again find the same thing. Okay. Good. Now, let's look at this definition of R cross P a little bit more carefully. If I have some mass moving with some velocity v, Newton tells me it's going to keep moving on a line with constant velocity if there are no forces acting on it, right? But my definition of L is R cross P. And R, as this object moves along this line, is always changing with time, isn't it? Right? R is the vector. You remember, it's the vector from the pivot point to the mass itself. So it's actually getting smaller and smaller. So how come angular momentum is conserved for this system? Let's see. Not only is R changing, if I look at the angular momentum magnitude, that Rp is R magnitude P magnitude times sine theta. Now, R is changing with time. R magnitude is changing with time. Theta is changing with time. So, for example, a moment later, my R vector will be this. P is going to stay the same. But now my theta has changed. But here's the nice thing. When I'm moving on this line, what is R times sine theta? R times sine theta is always the same. Because for all these right triangles, R times sine theta is basically the distance of the line to the pivot point, the closest approach of the particle to the pivot point. Okay? So R times sine theta is constant, so that angular momentum of a object that's moving with constant velocity with respect to any pivot point is constant. All right? So in other words, you can remember this L as the distance of closest approach times momentum. All right? That's what R cross P means. Yes. Well, okay. So I mean, it's obviously not a real formula, right? I mean, that's my way of saying times. Okay. Any questions? If you don't have any questions, it's my time to ask you questions. We're going to have a quiz. Okay. So let's have our quiz. And I will actually so you should see what the question looks like. Okay.